everyone. Welcome to the webinar on the 45Q tax credits for carbon capture. We'll get started in just a minute. So since it's talk, we will go ahead and get started. This is Alum with NARUC. I'd like to welcome everyone and thank all of our speakers, Doug Scott, Matt Frey, Walker Dimmig, Munson, and David Greeson. Thank you all very much for your time today. I'll pass it over to Commissioner Oden, the chair of the on Clean Coal and Carbon Management, for his introduction.
Thank you, and thank you, Kira, and all of the presenters. It's just an honor for us to get to this second part. I think the 5Q tax is going to be a very interesting topic for the next couple of months, and we are privileged to have the last presentation on this and understanding what's going to be happening on this tax. And so we want to thank Kira for all of her work on putting all of it together and finishing up. I don't want to take too much more time, so y'all sit back and listen. Doug, I'll hand it over to Doug Scott and let him get going.
Thanks so much, Commissioner Oden, and Kira, thanks so much for all of your help in putting this together. My name is Doug Scott. I'm with the Great Plains Institute, and I'm joined by my colleague Brad Crabtree from the Institute, and we really appreciate the opportunity to be with you again. As the Commissioner said, this is the second of two webinars following Congress's passage of the Section 45Q tax incentive reform, which has the possibility to propel a number of carbon capture projects forward. On the last webinar a couple of weeks ago, we heard about what was in the 45Q changes. On the next slide, Kira, if you could. What we're going to talk about today is translating that into technology and projects, and we have a really great panel to bring you information on that. We will hear from David Greeson from NRG, from Walker Dimmig of Net Power, and from Ron Munson from Cogentiv Solutions, as well as Matt Frey, who's going to talk about regional carbon capture deployment initiative that a state working group is proceeding with. So as the next three gentlemen talk, they're going to be talking about the technologies that they're pursuing and how 45Q might assist in those efforts. So let's get to our panelists because we certainly want to hear from them. We're going to start with David Greeson. David is the Vice President of Development for NRG Energy, and he heads up NRG's carbon capture program. He led the NRG team that successfully developed, financed, and commissioned the billion-dollar Petronova project that I know all of you know so much about. So David, we're really thrilled to have you with us today, and I'll turn the program over to you.
Well, excuse me. Thanks, Doug and Kira and Commissioner Odom for this chance to speak again about the Petronova project. I'm going to start with just a brief overview. I know that most of you have heard my speech about the Petronova project before, but just as a quick review, in case there's some on the phone who aren't as familiar with the project, I wanted to go through a quick overview, and then we'll talk about kind of what's next as far as commercial scale carbon capture goes and how 45Q is helping. Next slide, please. So the Petronova project came online in December of 2016, on time and on budget. If you click again for me. Over the past year, we've operated the plant. It has performed as we expected it to. It is performing as guaranteed by Mitsubishi. And we're capturing about 5,200 US tons of CO2 per day. And if you think about how plant availability is for the host coal unit and for the oil field and for the carbon capture system itself, if you take into account kind of outage time for all those, it ends up being that we think we can capture about 1.6 million tons per year on average which is about the same as taking about 300,000 cars off of U.S. highways. Could you click again for me, Kara? In the first year, we captured about 1.3 million tons of CO2. The plant performed actually very well. The problems that we had to take it offline for were largely unrelated to carbon capture. Hurricane Harvey affected our CO2 sink, the oil field, and so we were we're not able to produce CO2 for about 3 weeks due to that. We have an on-site cogeneration system that's making all of our steam and power, and that unit had various technical problems, so it had us out for a total of about 4 weeks last year as well. And then other miscellaneous warranty outages so that Mitsubishi could tweak things had us out the rest of the time. So the unit's performing very well. We're expecting that this year, after we took the final warranty outage, so Mitsubishi and its partners could clean up all the remaining warranty items. We just came back online after about a 6-week outage a few weeks ago. We think that this year we have a very good chance of hitting the 1.6 million for 2018. Click again for me. As I mentioned, our project is flue gas in and oil out. So in between, a lot of things are happening. We're making steam and power. We're capturing carbon dioxide. We're shipping it 82 miles to a oil field, and we're injecting it in the ground. But as far as how the plant economics work, there's flue gas in and crude oil sold to market going out. This oil field, before CO2 was injected, was making about 300 barrels a day, and after the first year of CO2 injection, it's now at 5,000 barrels a day. So had quite a bit of an increase, and that incremental production of oil is what's paying for the entire system. So if you click again for me, Kira. All right, so this project is 5 projects in one. If you'll click again. First step was for us to figure out and do the work to integrate into the host coal unit. If you'll click again. Then picking a carbon capture technology and getting it installed and getting it up and running in a way that met all of the pro forma requirements was the next project. If you'll click again. Next step is then to get that captured CO2 from the capture facility down to the oil field. We had an 82-mile pipeline that we developed as a private pipeline with not having condemnation powers. So we privately negotiated with about 160 landowners along that pipe to get to the oil field. And if you'll click again, the oil field itself was a conventional oil field, was not previously receiving CO2, and so we had to do a lot of work to get that field ready for CO2 and to go into CO2 flood operations. I'll give you a kind of rough magnitude here. The project in total cost about $1 billion. About half of that was spent on the pipeline and the oil field. The other half was on carbon capture. And if you click again for me, Kiera. Now this oil field was really, had been around a long time and had been in serious decline for the last 30 years. Consequently, the pipeline infrastructure to get crude oil from the field to market had been abandoned many years ago. And so the fifth part of our project to complete the cycle was to reestablish the pipeline link. Had about a 12-mile pipeline we built to get the oil to market. If you click again for me. So one of the tenets of this project, one of the drivers of doing this project was we wanted to show that you could do carbon capture if there was enhanced oil recovery available. You could do a carbon capture project without impacting the cost of electricity. And so everything we do out here, everything we did out here is paid for by oil revenues. If you click again for me. And in fact, in the electric market where this power plant operates, not only could we not use electric revenues to subsidize carbon capture, but we also had to not burden the power plant so that it continued to get the same dispatch and provide the same low-cost power to customers as it had in the past. So we feel like we accomplished that with this project. If you'll click again. And yeah, just keep clicking for me. We financed this with a group of partners. We did it with a double JV structure so that all the different entities that needed to invest in this project to get it done could invest in the pieces that they wanted to. NRG and our partners JX out of Japan own the Petronova Parish Holdings Company, which is the carbon capture and the cogeneration system at the power plant. This is also the entity that got a $190 million grant from the Department of Energy and a $250 million loan from the Japanese government through their two export credit agencies, one called JBIC and one called NEXI. Now this partnership owns everything that's inside the fence at the power plant. Outside the fence, we have Texas Coastal Ventures that owns both the West Ranch pipeline, West Ranch oil field, and the TCV pipeline, the CO2 pipeline. And here we have the Petronova partners owning 50% and a local privately held oil company called Hillcore that owns the other half and is the operator of the oil field. If you click again for me, Kiera. So I am sorry, that's my phone ringing. So the point of this panel is to talk about what's next. We've got this new bill out there, NIORI, and a lot of folks worked really hard on getting this this reform to the 45Q pass. Well, from my perspective, what does it mean? So I guess one of the hardest things to think about when you think about a next project is these coal plants are getting older, and many of them, such as the ones here in Texas, are in markets where natural gas, persistently low natural gas prices are putting a lot of pressure on the profitability of these plants. So one of the first things you've got to think about is if you're going to do a carbon capture project, does your host coal unit deserve the investment? Because it will be a sizable investment. The second big question is, can you actually monetize the 45Q tax credit? You know, a lot of the tax equity providers, the ones that have traditionally helped renewable energy projects monetize their tax credits, those guys are not familiar with carbon capture, and I can tell you, I'll go over it a little bit in a minute, they're kind of leery of the whole idea of carbon capture. So can we monetize those tax credits would be another big question. And then, of course, can you find a place for the CO2 at a price that makes up the difference? 45Q in enhanced oil recovery mode is $35 a ton, and as many of you have heard me speak before, the state of the art right now for amine scrubbing, post-combustion scrubbing, is around $60 a ton. And so at $35 a ton, we need another revenue source to be able to make up the difference. And so the question is, how do you get that? And can you get it from a company that has a good enough credit quality to bank on for either loans or equity investment? And then lastly, that very bankable loans, I don't see how these projects are going to get done by equity investment alone. The cost of that capital is just too high. And so in the non-public power world that I live in, I've got to look for some financing if I'm going to make these things work. Next slide, please. So who can monetize the 45Q credits? Well, you know, you've got to be a taxpayer and you have to have a real sizable tax obligation each year, or at least very consistently. So public power is not a taxpayer, and IOUs are not typically consistently taxpayers, at least not in the post-Enron era of the world. We've all got huge devaluations or write-downs of our assets that those losses, tax losses, are being carried forward. So it's it's a challenge to find folks who can monetize these for you. The 45Q, I know that the folks that were drafting the 45Q tried really hard to make it refundable, but it just wasn't possible. And so you've got to transfer these credits to someone who can actually turn them into an offset to their tax obligation. And I'll tell you, I have been, for the last month or so, in conversations with a number of the traditional tax equity entities, and so far none of them are really interested in talking to me. They say they've got all the wind and solar that they need, and for now they don't want to talk about carbon capture. Now, I've only talked to a few. I haven't talked to all of them, but so far that's been a little bit of a headwind in trying to monetize these things. Next slide, please. So the question is the incentive big enough? I mean, we've got all these things that I just talked about that are kind of pulling against making a project work, but if you're able to get through all that, is it even enough to get a project going? And I'll tell you that if the cost of post-combustion scrubbing hasn't come down at least what I would call significantly, 10 to 20% less than what the Petronova project cost, then the answer is no. What I think you can get from an oil company for CO2 payments and then plus the 45Q, I don't think quite gets you there. Certainly not for the hurdle rate that my company is looking for. I'm going to have some real cost savings if we're going to get there, and have the 45Q and the CO2 payments make up the difference. And then, of course, for straight sequestration, even if you're not doing enhanced oil recovery, the $50 a ton for 12 years, I still think it's going to be very difficult to work unless the technology providers can find a way to get the cost down. So if you'll click again, I think that that kind of covers my portion of this, and I think there's a Q&A session later, and I'll be glad to answer any questions. My email address is on the last slide here, and I assume, Kira, that these slides will be available to the folks on the phone. So if you have any questions after this that you'd like to talk about, I'd be more than happy to answer those, and I think that used up my 10 minutes.
Very good. Thank you so much, David. We really appreciate it, and congratulations on the progress so far with the Petronova project. Great to hear about that. Thank you. Next, we're going to hear from Walker Dimmig. Walker is with 8 Rivers Capital and also with Net Power. 8 Rivers is a technology commercialization firm focused on developing sustainable infrastructure of tomorrow. So Walker's going to tell us a little bit about Net Power, which is something that I'm sure you've heard about already, but I'm looking forward to the presentation. Walker?
Doug, and thank you to NARUC and Commissioner Oden for having us on this webinar. I'm going to spend just a few minutes trying to quickly give you guys a little overview of Net Power. I think many of you might be familiar with the company, but some might not. So, going to just touch on that for a few minutes, and then give you our perspective on 45Q and what we think it means for us and for our kind of deployment plans. If you want to go to the next slide, please. So just a little bit of a quick overview as to who we are. Net Power is actually owned by 8 Rivers Capital, CBNI, and Exelon. So Exelon, the Chicago-based utility, CBNI, a large EPC firm out of Houston. 8 Rivers, as Doug said, is a technology commercialization firm. The company is actually staffed mostly by seconded folks from those organizations. So many of us, still technically wear the hat of our home company. So I also work for 8 Rivers. Just a little bit about Net Power as a technology, just kind of a quick overview. Net Power is focused on natural gas commercialization of what's called the Alum Cycle. So it's an Alum Cycle. I'll explain a little more on the next slide, but it's an oxy-fuel supercritical CO2 power cycle. So entirely new power cycle, entirely new plant design around that cycle. Now, the Alum Cycle is applicable to coal. Net Power, as I said, is really focused on getting this technology deployed for gas first, which is really, I think, in our view, the first step for this technology. But there's also a lot of work going into advancing the coal version of it, working on all the coal-specific elements kind of in parallel to the core cycle being demonstrated by Net Power. So there are two parallel tracks there, and certainly everything Net Power is doing is relevant to the coal community as well. So the key highlights of Net Power, like I said, producing electricity from natural gas. We're targeting superior economics to combined cycle. Targeting a cost of electricity that's competitive with existing emitting plants. The Alum Cycle inherently captures or eliminates all carbon and non-carbon atmospheric emissions. And because that's sort of inherent to the design, it's not an additional cost to the overall plant or performance. We don't require water. There's no steam used here, so if we air cool, there's no makeup water required either, so we actually become a net water producer. The technology is the ability to use inexpensive fuels, so kind of all spec gases. And then it's more than just an electricity generation system. There are other valuable industrial gases that are produced as part of the process, and those can be very valuable to sort of the economic proposition of the technology. Turn to the next slide, please, Doug. So this is a very sort of simplified overview of the Alum Cycle. I'm going to go fairly quickly through this, but if there are follow-up questions, please do ask afterwards. But I won't talk about the technology too much today. Essentially, we're combining two things here. We're combining oxy-combustion and a high-pressure carbon dioxide, high-pressure, high-temperature carbon dioxide power cycle. So we see in the gray are the main kind of process, the main equipment, a piece of equipment. And then what you see, the lines you see running through are actual sort of flows throughout the system. And the width of those lines is proportional to their mass. So from an equipment standpoint, what you'll notice is, there's combustor and turbine. Those are actually, they look much like that turbine is a unique piece of equipment that Toshiba has been developing since 2011. It looks a lot like a gas turbine. But we're actually higher pressure than typical gas turbines, so it's got some steam turbine kind of pressure containment elements. We have a big heat exchanger train, and then we have some pumps and compressors, and those are sort of the primary equipment elements within the core cycle. You'll notice this big kind of orange loop is really the main kind of driver in the system. We've got a large quantity of CO2 flowing throughout the system, driving our turbine. And just the main thing I'll touch on right here is you'll see in the upper left, you've got a little bit of natural gas and oxygen coming in to this environment that is mostly hot pressurized CO2, reheated pressurized CO2 going into a combustor. Eventually, for the purposes of mass balance, we'll knock out the water because we want to get that out of the system and have pure CO2 for the recycle aspect of the system. We'll also need to knock out some CO2. Obviously, we have to have mass balance within the system. What I'll point out here is the width of that line, the lower red box there, red circle, compared to the width of the CO2 mass kind of being recycled in the system. That small export stream is what we put into a pipeline. And you'll see how small it is compared to the primary flow in the system. What that means really is for us to bring that CO2 export stream along for the sort of the compression and pumping ride is fairly trivial. We have these pumps and compressors in place to get the core power cycle to operate at the best possible efficiency. It also means we have the equipment in place to easily bring along this export stream for pressurization as well. So that's why we sort of call it inherent carbon capture. Whether we're emitting that stream up a stack or putting it into a pipeline, we wouldn't really change our equipment list, wouldn't really change our performance very much. So if we can get this core cycle to operate as efficiently as we believe it will, the carbon capture element is almost just coming along for the ride. Next slide, please. So this is just a little bit of a look at kind of how we kind of view the economic ecosystem. Now, to be clear, with the Alum Cycle, we are, like I said, we're targeting a competitive cost of electricity with combined cycle, largely driven. The two big drivers there are going to be efficiency and capital cost. So right now we're around 59% efficient. We see lots of opportunity for improvement there as well as this technology becomes more mature. And then we're targeting comparable capital costs to NGCC. Now, what anyone knows who's deployed technology, new technologies, is that we've got a cost curve to come down. We've got to deploy into the market at a higher cost than what we think this technology ultimately will get to. And so this is where all the other kind of industrial gases, this is where CO2 sales for EOR, this is where 45Q really come into play for us. Is if we can position this technology on sites where we can monetize those gases, monetize CO2, and collect 45Q credits, those are the opportunities that will help us to bring this technology down from its kind of first of a kind cost to an nth of a kind cost, which again we think is competitive with NGCC. The main byproducts you'll see there that we're able to sell are nitrogen, argon, potentially some extra oxygen, and then CO2. The nitrogen and argon come from an air separation unit that we build on site that provides our oxygen for oxycombustion. And so that unit can also produce those gases for sale as well. If you look at the little CO2 box there where it says about $49 million of annual revenue, there's a green line and an orange line going into it. The green line is the 45Q revenue that we've calculated, at least potential revenue, and the orange line is CO2 sales for EOR at about $15 a ton. And I think that breaks down the CO2 line. The CO2 sales line would be about 13.7 million on its own. So obviously you can see 45Q has a big impact there in driving CO2 to being a sizable income stream for one of our projects. Next slide, please. This is just a little bit of a look at how we sort of see ourselves fitting into the kind of the future system and how we think any kind of new carbon capture technology will fit into the overall system. What we're looking at here is kind of how trying to understand not just on a point cost of electricity basis that but more on a system-wide cost of electricity basis. What kind of technologies should we be targeting in order to get the mix we need to have deep decarbonization with also acceptable cost of electricity for consumers. So this is based on a study that was done by Steve Brick and Sam Thurmstrom. It's in the Electricity Journal. They basically took actual costs from Germany, California, and Wisconsin, and then collected data as on kind of system-wide electricity costs as you start sort of increasing your renewable portfolio standard in order to get to higher CO2 reduction levels. And essentially, if you look at the very bottom point there where it says 100% NGCC, that's just if you took the natural gas blended costs from all those regions, you'd get about $60 a megawatt hour, but you'd have no sort of CO2 reduction. And then what we do is we blend in, what the study did is it blended in renewable costs as you wanted to go up this sort of CO2 reduction chain. And what they observed and what many other studies have observed is ultimately you're actually overbuilding your renewable portfolio in order to get kind of diminishing CO2 reduction returns. And eventually you hit a point where you're not even really decreasing the overall gas you're putting into the portfolio as a backup. Now that gas could be other technologies as backup, but the point is you're getting to this system that is far overbuilt. So from a system-wide standpoint, I can look at technology to technology and compare costs. But when I look at it overall, in order to really get to higher decarbonization levels, you're going to need to be able to mix something, or it would behoove everybody to mix something like a low cost, gas or coal with carbon capture in there as a flexible complement to these growing renewable portfolio standards. Next slide, please. So where are we with this technology? We sort of two different tracks here. We've completed construction and are in kind of startup and early testing of a demonstration plant. It's a 50 megawatt thermal plant down in LaPorte, Texas. It's a full Alum Cycle. The only thing it doesn't have is we didn't build an on-site air separation unit. That didn't need to be proven as a piece of equipment. It's very well proven, so we're pulling pipeline oxygen for the demo plant. but we otherwise include the ASU's capital cost and parasitic load in all of our sort of commercial scale pro formas and evaluations. It's about a $160 million program, not counting the turbine, which Toshiba has developed as their own separate R&D program. And yeah, we finished construction at the end of last year, so we've slowly been working our way through startup and early testing of this technology, and hope to have some exciting milestones and reports to provide you all at some point in the future here. At the same time, we've been working on the design for commercial plants and doing early development activities. So we completed a pre-feed of that of a 300 megawatt commercial facility. We've identified several sites. We're continuing to look for more siting opportunities, and we're trying to we're starting to bring projects together around those sites with the goal of if hopefully having a plant online, kind of delivered by the end of 2021. Next slide, please. So here, to get to 45Q, the kind of key considerations that we look at, like I said, the revenue stream we look at from CO2 now is about $49 million a year. When we run our project economics, we really do feel that 45Q, if the technology delivers as we hope, 45Q gives us a very strong economic case, and so it really turns a lot of the project into kind of project development risk. How much value can we extract from 45Q, and how do we deal with kind of new technology risk? But 45Q goes a long way towards basically building a really solid economic case for these facilities, even at kind of first of a kind and serial number 2 costs. We also think it creates, an opportunity away from EOR. We previously would not have really been looking at direct sequestration projects, at least early on. And with the $50 a ton available for those projects, we do think some of those will make sense. Like I said, it's really, for us, it's all about providing a pathway to move down a cost curve. And we think it gives us sort of the economics we need to do that. It enables us to otherwise untether more from sort of specific CO2 or produced gases or co-produced gases kind of opportunities. And what I mean by that is, given where we kind of see first of a kind, our first plant economics coming in, our siting constraints were really limited to where we could truly maximize every one of those industrial gases to make a project work. With 45Q, that enables us, it gives us a little more leeway to not have to find the very kind of specific niche areas where all of those gases are monetized, or, kind of monetizable for sort of the maximum end of their range. We're also hopeful that what the timeline of 45Q is going to lead to at least an acceleration of orders. If we meet our first of a kind plant timeline, we think there's going to be obviously a big incentive there for folks to try to get in ahead of that 2024, the end of 2023 being 2024 deadline for 45Q eligibility. So the questions we're focused on right now, similar to David mentioned, our IRS guidance is where we think some things need to be answered still. We're working with the Carbon Capture Coalition, which is the former NARUC group, to address some of these issues, as well as working with others. But the big ones we see are sort of permitting and permanent geologic storage kind of definitions requirements. That there's some uncertainty there. There's some open-ended recapture language that the IRS needs to comment on. That certainly drives some the value of the 45Q tax credit kind of in the market, depending on how much kind of risk there is there. Ensuring the commenced construction definitions are very clearly laid out and follow prior kind of precedent. Those are the big things we're looking at there. Project structuring, it definitely there's some new complexity that's sort of added in. I think one way compared to the way sort of the wind credits have worked, there are other players, other taxpayers brought into the project mix, and so we do think that will help. But there's definitely a lot of complexity there, and understanding the tax appetite for all those players, especially given an environment where the corporate tax rate is now has been lowered, definitely changes that dynamic. And finding the right partners on projects that have internally tax appetite is something we're focused on. And then, as David mentioned, the role of sort of the financial institution and tax equity players. Tax equity markets are challenging right now. Our understanding is folks are hesitant to get into kind of new tax equity, new credit structures. It's enough to sort of have educated the market enough about kind of the existing credits and gotten them comfortable in those projects. So there's definitely going to be a lot of work to do for the carbon capture community to kind of educate those players, get some model projects running, and have sort of demonstrate kind of a precedent for the success of these structures. So a lot of work to do there, but again, we still think this 45Q it's a great opportunity, and we think it's going to help us move forward in ways that without it would have been even more challenging. So that's all I've got for today, I think, Doug.
Yeah, thanks, Walker. Appreciate it very much. Very exciting and technology on your end too. We appreciate the presentation. And next, we're going to hear from Ron Munson. Ron is a principal at Cogentiv Solutions. In addition to that, Ron has been the global lead for carbon capture at the Global CCS Institute since September of 2014. And prior to that, for quite a number of years, was a senior environmental engineer at Tetra Tech. So, Ron, great to have you on board, and look forward to your presentation.
All right. Well, thank you, Doug. I appreciate it. The material I'm going to present today takes a little bit of a step back from what David and Walker have presented. Looks at carbon capture more broadly, gives a little background on what CCS is, some of the chemistry and physics that underlies it, and explains why there are some of the challenges with it that there are. Talk a little bit about how it has been applied and how it might be applied in the future, with a focus on industrial applications. So next slide, please. Just a little bit of background on Cogentiv Solutions. It's a consulting firm that focuses on carbon, energy, and environmental management. I'm located in Washington, D.C., and in the carbon management space, I work on carbon capture as well as carbon utilization and reuse. We work for governments, non-governmental organizations, industrial organizations, and we help develop and design and manage R&D programs, and develop advocacy products, and work on project design and development as well. Next slide. So looking at carbon capture a bit more broadly, the International Energy Agency has said that CCS is one of a portfolio of approaches and technologies that are needed to meet the greenhouse gas emissions targets that were established in Paris that call for limiting global temperature increases to 2 degrees C. Their modeling has shown that about 12% of the total reduction in greenhouse gas emissions is projected to come from carbon capture and storage. The reductions are projected to come from both the power sector, which accounts for about 40% of global emissions, and from the industrial sector, things like steel, cement, fertilizer, and petrochemicals, that sort of thing, which produce nearly 25% of emissions. If you look at the projected distribution of those CCS-related emission reductions, a little more than half, or about 55%, comes from the power sector, and a little less than half, about 45%, comes from industrial sources. Next slide. Now, you hear 12%, and that really doesn't sound like very much, but the Intergovernmental Panel on Climate Change evaluated 11 different scenarios for achieving the targets that were agreed to in Paris and found 2 things. The first is that if you don't include CCS among the options to achieve the targets, it's impossible to reach the goals for 7 of the 11 scenarios. And in addition to that, for the scenarios that were able to meet the goals, not including CCS as one of the options, more than doubles the cost. So it's a pretty important thing to include in your forward planning. Next slide. So let's take a closer look specifically at the capture step. At a basic level, carbon capture involves separating and removing CO2 from a gas stream before it's emitted to the atmosphere. The top left section in this graphic shows that if you start with pure nitrogen, which is designated by the blue dots in the figure, and pure CO2, which is designated by the green dots, put them in a box and have them separated by a divider. And then if you remove the divider, the nitrogen and the CO2 will spontaneously mix. This is basically the situation you have in a power or an industrial gas stream. The gas separation process is illustrated in the lower left section and involves re-separating the carbon dioxide and the nitrogen. This separation requires the input of energy. The graph on the right side shows that the energy required to separate the gases increases really quickly as you decrease the amount of CO2 or the partial pressure in the gas stream. This effect of increasing energy requirement with decreasing CO2 concentration is important because gas streams in different industries and applications have really diverse concentrations. Next slide. And we see that in this graphic, which shows the variation in concentration across different industries and different applications. So here we see that the concentration of CO2 in air is pretty low, about 400 parts per million. Separation from air would require a lot of energy, based on what we saw in the last graphic. Concentrations for gas-fired power production are around 100 times higher, around 4%. They increase more for coal-fired power production, and then are slightly higher for cement manufacture and steel production. There's a pretty big jump in CO2 concentrations for gasification-based processes in natural gas streams and in ammonia production. Going back to what I noted before, the energy required and therefore the cost is lower for these higher concentration gas streams. Next slide. So let's look at how that has played out so far in actual applications. This slide shows both the history and the future of full chain, large scale carbon capture and utilization projects. The blue dots here represent projects that are storing CO2 using enhanced oil recovery, whereas the green dots represent projects that use deep saline storage. The different horizontal lines moving across the figure represent different sectors where CCS is applied. There are a few things that are important here. First, CCS projects have been in operation for a long time. You often hear that it's an experimental type of technology, and it's really not. Enhanced oil recovery-based projects using captured CO2 have been operating since the early 70s. And the Sleipner project in Norway has been operating for over 20 years with dedicated storage in a deep saline formation. So these projects demonstrate long-term safe capture and storage. Another important component of this graphic is that the vast majority of operational projects involve capture from industrial applications, most notably in natural gas processing. The other industrial applications that have associated projects have some things in common as well. Most important is that they have high concentration or high partial pressure gas streams. The energy required to separate the CO2 from these streams is a lot lower, and so the costs for separation are lower as well. The top line in the chart represents the power sector, where we have the Boundary Dam project in Saskatchewan and the Petra Nova project that David talked about earlier. And then looking forward, there are several more facilities that are slated to come online in the next year or two. Next slide. So if we go back to this figure that I showed previously, what we see is that most of the projects that are operational, they're industrial projects that have high gas concentrations. So gas concentrations to the right of the black line showing there. Remember, higher concentrations of CO2 mean that the energy requirements and the cost of capture are lower. Can you advance it, please? And so if you look to the left-hand side, we're just now starting to see projects in sectors to the left of that black line, and they've all required substantial public sector support. Next slide. So clearly, CCS on industrial sources represents a significant opportunity for applications. In 2014, the National Energy Technology Lab conducted a cost analysis of industrial CO2 capture. The principal metric that they were interested in was the break-even cost in dollars per ton, or the selling price required for recovery of all costs for separation, purification, and compression. This graphic summarizes the results, with the break-even cost on the vertical axis and the volume of CO2 potentially available on the horizontal axis. The different colored lines are associated with particular industries. So what this tells us is that for CO2 from natural gas processing, the break-even price is about $18 per ton. For ammonia production, the available volumes are a lot lower, and the break-even price is just under $30 per ton. Larger volumes, if you look at the green line, are available for ethanol production, and the break-even price there is around $30 per ton. The take-home message here is that industrial applications really represent the low-hanging fruit to spur CCS deployment. Next slide. Now, the cost is a significant issue for these technologies in general, and as David talked about as well. But what we've seen over the last 10 to 15 years is that we've already seen substantial cost reductions in CO2 capture. In 2005, there was a Harvard study that was done that estimated capture costs at over $100 per ton. And in 2012, we were seeing estimates that were closer to the $60 per ton estimate that David mentioned earlier today. And the R&D program that the Department of Energy is pursuing is trying to push those costs even further down to $40 per ton, and hoping that those technologies that can achieve those kinds of costs will be available in the 2020 to 2025 timeframe. Most of the cost reductions that we've seen so far are associated with reductions in the energy penalty, or how much energy you have to put into the system in order to run the carbon capture system. Again, looking at the different values, if you look at the 2005 value, the energy penalty associated with systems at that stage was over 30%. By 2012, that was down to around 20%, and I think that's consistent with what they're seeing at Petronova. Some techno-economic analyses that NETL has run indicate that currently you're down to around 14% energy penalty, and if the targets that they've established are achieved for the technologies moving forward, you'll see energy penalties down at around 9.5% by 2020. So the costs have the potential to decrease, but more work definitely needs to be done. Next slide. So what are the implications of this in light of 45Q? Well, industrial sources represent about 80 million tons per year with break-even costs of less than $35 per ton. And so, that's clearly a significant opportunity there. On that previous graphic, it showed break-even costs for hydrogen production that were fairly high, but I think that that's an artifact of the way that the analysis was done. And I think moving forward, we're probably going to see opportunities for carbon capture from hydrogen production as well. In the next few years, we'll see data coming from the Quest project in Canada that will give us a better indication of what the capture costs are associated with hydrogen production systems. So great opportunities. The challenge comes with accessing EOR or storage. And so, that's a hurdle that these industrial sources are going to have to try to overcome. But that being said, these low-cost sources are likely to be used before power sector sources and be able to take advantage of 45Q sooner. If you do look at the power sector, those higher costs associated with capture are an impediment right now, and that's consistent across most things. There's an interesting analysis that has been done by the Clean Air Task Force that hasn't been released yet, but will be in the next 3 or 4 weeks. And in that analysis, they've taken a look at the potential for deployment of carbon capture systems given 45Q. And so it just assumes that all of these low-cost industrial sources will be used first. It takes into account the CO2 EOR supply curves, and based on that, what they've seen is that 45Q alone will incentivize about a dozen or so power production facilities to deploy carbon capture. They've also looked at some other incentives that are being considered in Congress right now, such as private activity bonds and master limited partnerships. And if those incentives are available as well, that number goes up to 80 or more. And so, you know, there's real opportunity there as well moving forward for the power sector. And that's it. Go ahead and next slide. That's all I have. As David said, if you have questions for me, I'm happy to answer them now. Or if you have questions later, you can contact me at the email address that's on that slide. Thank you.
Ron, thanks so much. And to wrap up for us, we're going to hear from our friend Matt Frey. Matt is with Governor Mead's office, and Matt's going to talk about regional carbon deployment initiative, trying to match sources of CO2 to purchasers, and it follows nicely from Ron's presentation. So Matt, take it away.
Thanks, Doug. Thanks, commissioners and everybody for having me back. I'll run through this fairly quickly, see if we can leave a few minutes for questions at the end. But as the previous speakers talked about, they gave real valuable insight on capture technologies and that they worked on and so forth, and excuse me, the benefits of 45Q to these technologies. So I'm going to shift directions just a little bit and talk briefly about what we're doing to try to better regionalize this CCUS technology and a hope to expand deployment across the country. So with that, as I talked about several times in the past, what I and many others believe to be the next limiting factor in CCUS deployment, excuse me, is the ability to transport that CO2 from sources to sinks. And that's what we're looking to address with this deployment initiative. So just in summary, there's myriad CO2 resources out there that could provide value to both industry and the environment. But to date, we haven't put together real comprehensive information that shows the locations of all of these sources and sinks, nor have we put together any real logical pipeline routing opportunities to connect the two. So with that general baseline challenge in mind, we took this to the governor and discussed it with him, and he instructed the work group, which is what I mean by we in this conversation, to see what we could do to address it in an effort to further deploy CO2 or CCUS technologies. So just kind of generally, I won't run through this in detail, but generally what we're looking to do is work on deployment initiatives in 2 general regions, one being the Northern Plains and the Rockies, and the other being the Midwest regions. In an effort to support this initiative, back a month or 2 ago, Governor Mead sent out a letter to 17 governors across these regions, asking for their active support in this effort, as well as their participation as we move forward. So with that baseline, we're in our scoping phase right now and moving forward on the initiative. Just generally how we intend to approach this is in a 3-phased approach. The first phase would be the scoping, which I just said that we started in. We're going to look at baseline mapping of sources and sinks across the regions, try to look at some analysis for cost to get early projects going forward, do some pipeline modeling to give generalized routing opportunities for pipelines from sources to sinks. And just to be clear, as I've said in the past, we're not looking at this at a project level. It's too complex and too expensive to do that. So we're just trying to give some opportunities to facilitate development in the future. Additionally, what we're doing now is outreach to governor staffs in the 17 states, basically see how they want to participate and whom they want to participate from their states in this initiative. And also we're looking at what other state and industry stakeholder participation will be asked for. We'll invite folks to participate in this. Next phase, phase 2, is we'll take this baseline information and start carrying on some meetings in the regions to see how folks think that we can take this information and move it forward into a final product. And then the final 3, the phase 3, we'll have some final modeling and planning support for project development, which we hope will further facilitate projects. And then we'll with that final product in mind, we'll look at other policy options that can help facilitate these project development, as well as bridging that additional cost gap in an effort to get these projects moving within the timelines of the 45Q tax credit. And I went briefly. Hopefully there's a few minutes for questions.
Great, thanks, Matt. So open up the floor for questions that folks have.
Yeah, this is Kira. I have a question coming from Commissioner Tom Johnson from Ohio. I guess this question could go to Ron potentially, but anyone is welcome to jump in and answer it. He wanted to know if there is such a thing as enhanced natural gas recovery. In other words, is there any technology or methods that can apply the concept of enhanced oil recovery to natural gas production, since Ohio is such a big shale gas producer?
Yeah, there is a process that is called enhanced gas recovery, or EGR. It isn't as mature as enhanced oil recovery, but it certainly does exist and has potential for another revenue option for captured CO2 for sure.
Other questions?
Doug, let me ask one. This is Jeremy Oden. Sure. I was wondering, and I guess it's either David or Ron, I'm not for sure which one of them mentioned, what other things is Congress looking at that the 5Q can be combined with to sort of stimulate some of this financial side of getting involved? Do we have anything other than, just the regular incentives that are out there working?
Yeah, well, the ones that I'm aware of, and there are probably more that I'm not, but they're looking at private activity bonds and master limited partnerships, and with those, I think that would enhance the ability of project developers to get financing if those two things were available. And I'm sure there are other people that can address that better.
This is Doug, and I was just going to jump in and say that the state working group has also identified infrastructure help with pipelines as something that could be helpful to the process as well, and specifically more in the oversizing of pipelines when they're first built. That's certainly not economic at the beginning, but something where in order to enable more people to sign on later on, trying to get some of these pipelines built. Hopefully that's something that, if there ever is an infrastructure bill heading through Congress, that's something that could be included in that.
Good.
Yeah, this is Matt. Just to add to that, Senator Barrasso and Senator Whitehouse just introduced the Use It Act bill 2 weeks ago or something to help facilitate this pipeline development that we're talking about.
Thanks, Matt. I do want to say, with respect to master limited partnerships, there was an issue that came up during the last webinar concerning a FERC ruling that was not allowing return for a cost of service tariff in addition to the master limited partnership. And so that case is winding its way through. It's my understanding that most of the pipelines that would be involved in CO2 wouldn't be owned by utilities themselves. And so what the FERC was trying to do was eliminate the situation where there could be kind of over recovery, almost a double recovery situation. With the MLPs, the benefit of that is that the tax doesn't apply to the corporation, but it applies individually to the partners who are part of the partnership. And the feeling was that allowing that tax benefit to occur, which is why people are trying to get MLPs passed for carbon capture projects, to allow that recovery as well as cost of service return on equity recovery would be too much. But when the state working group was putting together their paper, and looking for ways to enhance the projects, they weren't looking at double recovery in these situations. They were just looking at the tax advantage of MLP versus traditional corporate tax structure. So, there still can be the benefit of having the MLP. There just isn't kind of the double benefit of having MLP plus cost of service recovery. Kira, I know that was something you had asked about last time, so I want to make sure we got to that.
Yeah, thank you so much for the update, Doug. And since it is 3:01 here on the East Coast, I'm going to close this up. Thank you to Doug and all the panelists for taking the time to speak with us today. I'll be posting a recording of this webinar as well as the presentation slides on NARUC's website, Thanks very much, everyone. Good afternoon.
Thank you.
Thanks. Take care.